And where were we? So last time we were here. Okay, so we were talking about these standard candles and how it's extremely difficult and important to figure out the distances to objects. To know their positions in the sky is fairly easy, just measurement of angles. But knowing their distances, whether they are nearby or far away, is extremely hard. And for that, either you measure parallaxes or you find something which can be made into a standard candle so that you measure their flux. Okay, so you measure their flux, you know their intrinsic luminosity, and the fact that flux equals luminosity divided by 4 pi distance squared will let you calculate the distance. Okay, so this is done. Now, so we are actually, so here we are sort of starting from the large scale, we are starting galaxy formation from the cosmological context. Okay, this is not always the case, but I think that it's a useful way to introduce galaxy in a course on galaxies. Okay, so let's see. So we have sort of heard in the previous slide about a way to measure distances to standard, measure distances to say galaxies or stars. Now, what else do we need? The biggest discovery in galaxies is something called Hubble's law, right? The fact that other galaxies are moving away on an average from us, and in fact, not just that, the farther the galaxy is, the faster it is moving away from us. Okay, so what do you need in order to figure this out? You need distances, right? And you need their velocities, right? Because you have to plot v versus distance. That's what will give you Hubble's law. Okay, so we have figured out how to find distances to galaxies by locating, say, Cepheid variable stars in nearby galaxies. This can only be done like in nearby galaxies. Okay, but if you have to move beyond type 1a supernovae, is what we talked about. Okay, so how do we measure the velocities? And the technique there is Doppler shift. In fact, it's such a powerful thing. Doppler shift is such a powerful thing that even if you're speeding on the highway, it's the same principle essentially that can actually be used to measure your speed. Although there it's perhaps just the travel time. I don't know if they use spectra, it's just the travel time. But in principle, this applies everywhere. And it's as simple a phenomenon as, like, the ambulance approaching towards you, the pitch sounds sharper compared to the ambulance receding from you. Okay, so this formula is the formula that relates the intrinsic frequency of an emitter, right, like an emission line or something, and this is observed frequency. And this is basically a simple application of special relativity, right? You can actually see this is almost like the transformation of a 4-vector in special relativity, right? This is like a gamma factor, 1 over 1 minus v squared by c squared is gamma. So nu observed equals gamma nu times 1 minus the line of sight velocity divided by c. So here is the geometry. So this is the observer. This is an object which is emitting, and this angle theta is this angle. So if theta is say smaller than 90 degrees, the object is moving away from you. So the observed frequency should be lower than the actual frequency that the object is emitting. So this basically corresponds to this situation. Now, yeah, so this is basically a Doppler shift. Okay. Now, what about how can we use Doppler shift for learning about the velocity of galaxies? So what you need is some features in the spectrum of a galaxy. So you want to sort of look at if there are some universal features in the spectra of galaxies. Features meaning, say, emission lines, absorption lines, things like that. And by Doppler shift, what we can see is whether the position where you expect the emission and absorption lines to be, are they appearing shifted? So that shift will case where V is much less than C. So for the nearby galaxies, and nearby, I mean, it's actually not that nearby, like, reasonably far away galaxies, V is actually much less than C. Okay, so you can actually ignore these complicated gamma factors for the nearby universe, right? Redshift much less than 1, which is actually a significant volume of the universe around us. Okay, so here is the person, Slipher, who mastered this technique of obtaining spectra of galaxies. Okay, galaxies are extremely faint and diffuse objects. And so what do you need in order to produce a spectrum? You need a lot of, like, bright enough light, and then you need to spread that light into its different colors, or you need to uh, disperse the light into its frequency or wavelength components. It's sort of, this is what a prism does. Okay, but galaxies being too dim and diffuse, it's a very technically challenging job. So this is the person who sort of mastered this art of measuring galaxy spectra. And so this is like in fact, he is the one who measured the velocity of Andromeda galaxy, our nearest big galaxy, to be minus 300 kilometers per second. So minus means it's coming towards us. So blue shift is negative velocity, according to the convention. Red shift is positive velocity, things which are moving away from us. So here are some spectra measured by someone called Humason. In fact, Humason worked at Mount Wilson Observatory. In fact, he was working in the group in which Hubble was the boss. In fact, I was actually reading the history. He was a janitor, the person responsible for cleaning the premises. So he had almost zero education, but he was someone who was like interested in this kind of stuff. He was very patient, and you need a lot of perseverance to do this kind of things. So without having any degree, forget about PhD or masters or whatever, he sort of mastered this technique and was able to obtain beautiful spectra, observing daily at night at the telescope at Mount Wilson. So there are a lot of such examples where, especially in this kind of area where the finesse required is extremely high, and where a lot of hard work and perseverance is needed. Okay, so here is an example. So this is a galaxy NGC 221. So let's say, before that, what is NGC? Do you guys know what are these names here? Yes, so NGC stands for New General Catalog. There are Messier, there are Messier Galaxy. M31 is the name of Andromeda. So there is NGC, and there are others, Henry Draper Catalog and whatnot. Okay, so these are just sort of, yeah, you should know about it. Okay, so let's see what is being shown here. So this is the optical appearance of the galaxy. This in the middle is the spectrum, observed spectrum of the galaxy, and you see these it's a spectrum. It has everything, whatever there is. So these things, yeah, dark shows emission, and this gap in white shows absorption. Galaxies have absorption features in their spectra. Okay, and we'll come to that why that is the case. But these are these absorption features, and they're most likely, say, hydrogen like Balmer like feature, or some some very common like calcium like feature. But the point to notice, so, and the top and bottom here are the expected location of these transitions. So if you read the history of solar spectroscopy, looking at the spectra of the sun, Fraunhofer just sort of looked at sun's spectrum and identified very strong absorption lines, and they are the famous A, B, C, D, H, K lines from the sun. So at that time, no one knew what they were, but eventually we mapped them onto elements and their ionic states. For example, the sodium D line is because of excitations in a neutral sodium atom in sun's atmosphere. So the atmosphere of stars are cooler than their photospheres. So that's why that cooler gas absorbs the underlying brighter light. So that's why you have these absorption features. Okay, so let's see. This is a galaxy, another one. These are all galaxies in our neighborhood, so to speak. So this is the expected position. So x-axis here is wavelength. Okay, the x-axis is wavelength. This red arrow shows the expected location of that particular line. So you see this, it's the second, right? So, right. So this is the expected location, and this is the measured location. I think it's the second absorption feature here, which this arrow is marking. Okay. Now, what is shown here is that in this case, the spectrum, the observed spectrum is shifted on the left compared to all the other cases. And that's why the velocity that you infer is negative. So this is a galaxy which is coming towards us rather than moving away from it. Most galaxies, if you go a little farther out, are receding away from us, right? That's because, that's what Hubble's law means. Now, if you look at this is a galaxy which has a velocity of 2,300 kilometers per second. Positive sign means redshift. That's the convention. This is how it appears. This is, you actually just track this feature, okay? This feature is here. I mean, it's much brighter here. It's perhaps a nearby galaxy. That's why you can accumulate a lot of light. This feature goes here, 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 and here. And the farther you go, the dimmer the actually observed spectrum becomes. That's also very natural, right? The flux that a telescope measure goes like 1 by d squared, where d is the distance. The interesting thing to note is, there's a trend in velocities here, right? So minus 200 is coming towards us, and there's a progressive increase in the recession velocity in this sequence. Okay, and this recession velocity is measured by this shift in the wavelength, right? You're just sort of applying this formula trivially in the limit that v is much less than c. You can just make this 1, and basically delta nu by nu naught. Delta nu is the shift in frequency, or shift. Delta nu by nu is delta lambda by lambda, change in frequency, relative change in frequency or wavelength is just v by c. Right? And if we assume the line of sight, if we just define v as the line of sight velocity, which is just v cos theta. Okay, so this is just a trivial application of this. You can actually see the shift in wavelength here is small and here it is big. That's why velocity is proportionally bigger. So that's it. Okay, so now if you have any question, yeah, please. Right. So the red arrow shows the the shift in the observed spectrum relative to the reference spectrum. So these are reference spectra, right? The locations are the same for the top and bottom reference spectra shown here, right? And the nature of this spectrum, even by eye, without knowing any physics, you can actually sort of figure out that there is this, and then there is a lot of light without any break. So you're basically saying it's the same thing, same sort of a type of a star. It's just basically moving faster away from us. That's why giving a larger shift in the spectrum. Yes, this velocity is with respect to us, the telescope. Okay. Okay. So now we have method to figure out the distance of the objects, say by using Cepheids. We have a method to measure velocity, line of sight velocity of galaxy. I mean, if you have two variables, what do? You just plot y versus x. And this is Hubble's famous diagram, this is the line of sight velocity, like measured by techniques pioneered by Slipher and put in practice by Hugh Mawson, his assistant, and then put together by Hubble. So you see V versus distance, and this is distance in parsecs. These are the data points. This is 0. So positive means the galaxies are moving away from us. And there are some galaxies which are falling towards us. You know, they have a line of sight velocity which is negative. But the farther you go, you know, almost all of them are going away from us, right? So this, you know, this distance is obtained from Cepheids, use of Cepheids as standard candles. This is just the spectra, galaxy spectra. Okay, so this just shows the farther the galaxy is, the higher their recession velocity is. So the picture is that we'll actually come to the picture, but it essentially means that the universe is expanding, right? Okay. So here you can actually see they are able to measure distances, you know, velocities of order 1,000 kilometers per second. And you see units are kilometers, not per second, but you know, I think at that time they didn't have Python and stuff, so you know, it perhaps was not that easy to make the figures very high quality. Okay, so and this is of course the Hubble Space Telescope, named in his honor, because this is perhaps one of the biggest discoveries in science. Okay, so what is the implication of Hubble's discovery? So this is a diagrammatic. If you have any question, you know, feel free to. Okay, peculiar velocity. Right. So in this the simplest picture of the universe with expansion, you can say that everything is just sort of expanding away from each other. Peculiar velocity is the velocity relative to this Hubble expansion. For example, nearby galaxies are affected by the gravity of our Milky Way galaxy. They're sort of pulled in, like M31 Andromeda galaxy is pulled in, and it does not satisfy Hubble's law, right? Because it's affected by this overdensity of mass, and that's what is, you know, causing this peculiar velocity. So galaxies have two velocities. One is this Hubble flow, and on top of that, due to local inhomogeneities of mass and gravity, the peculiar velocity. Okay. Any question? Yes. Yes. No, I didn't say dimmer. It's not necessary that it has to be dimmer. I didn't say dimmer, right? I mean, it appears that yes, the farther you go, they are dimmer. Yes, absolutely. It can be. You can have a small galaxy which is nearby, but dimmer. That's why it's dimmer. Yeah. All that is possible. Here, what I'm saying is, we just ignore this guy. We are not really using this for anything. We are just saying, oh, there is a galaxy here. Let me measure the spectrum of this. This is how the spectrum looks like. This is the how much I have to shift in order for it to put on top of the reference spectrum. So that gives me V by C, the recession velocity. That's it. We are not using the fact that, you know, it is dimmer or bigger or anything. You understood? This is just to show you which galaxy they are. This information is not used in this. What is used is spectra, right, from the previous slide, and the distance from Cepheids in these galaxies. Got it? Okay, so what are the implications of Hubble's discovery? Basically, this is what is shown here. So you have the sun or Earth, whatever, us, and the closer in galaxies are moving away slowly. The farther the galaxies are, they are moving much farther away. And so, for example, then the nearby galaxies will not be redshifted as much. Farther away will have a higher redshift because they are moving away faster. They are moving away faster away from us. Okay. Now, this cannot be the right picture because this puts the sun at a very special place. It's the whole the discovery of all of that Earth is round and everything goes against the fact that we are at a very special position, right? So this whole Copernican revolution suggests that we're not in a special place. So this is not the right interpretation of Hubble's law. That's right. So right. So this cartoon is in fact what is sort of a good a more physical interpretation of Hubble's law. So this is the present day universe. Okay. And as you go back in time, see, things are moving away from each other. If you just go back in time and sort of do your simple dv dt or dx dt equals v, you can actually say that these things which are moving away were closer in as you go early in time. Okay, and so actually the other thing is you can actually measure this slope between velocity and the distance, and that slope is called Hubble parameter h0. Okay, he obtained a value which is not quite accurate, right? The present value is about 70 kilometer per second per megaparsec, and this is a weird unit actually. As you can see, there is a distance unit here, kilometer, and a 1 by distance unit here per megaparsec. So these units actually cancel away. So h0 is just 1 by time dimensionally, but we use this because it's a very sort of easy. It provides an easy way to interpret what it means. What it means is that if you have a galaxy which is 1 megaparsec away, it should be moving away from us at meter per second. That's why we adopt these, non-physicsy looking units. Oh, yes, yes. From which formula? This formula? No. This is basically dominated by the peculiar velocity. So Andromeda is so nearby that this term for Andromeda is much smaller than this term. No, this is positive. Hubble's velocity, Hubble law gives you a positive velocity. Peculiar velocity can be of any sign. In the case of Andromeda falling towards us, it's a negative sign. It is not a constant, absolutely not. You see these 1, 2, 3, 4 galaxies here, they are perhaps neighbors of Milky Way which are falling towards us. Okay, cool. Right, so this is the interpretation that things started small and they sort of expanded. And of course, if you extrapolate things too far away, everything collapses to a point, and that sort of give rise to this whole idea of Big Bang, that the universe is not a steady thing. It had a definite beginning, and it is evolving in time. Right? Normally, when we do physics, we sort of do steady models and so on. But surprise, surprise, our universe itself is not a steady state system. It had a beginning and perhaps an end. It will have an end. This is another way of looking at interpreting Hubble's discovery, that you take a balloon and if you inflate it, make it bigger. So as you can actually see, any 2 points on this grid, a smaller distance when the balloon size is smaller, and as you blow it and make it bigger, the points move away from each other, and farther the points are, the velocity between them is larger, right? And here, it also shows that if you have a wavelength, wave shown here, say, some electromagnetic wave, that wave also gets stretched because of this expansion. Okay, so this is called cosmological redshift. So these are all important. I'm just giving here a very qualitative description. In your other course, which is on the board, you will get much more quantitative with this. But it's a good idea to have this qualitative story in mind before getting into Christoffel symbols and things like that. Okay.
The Doppler shift that was being measured by Hubble's team, it was cosmological redshift, right?
It was everything, right? But the farther you go, it's dominated by cosmological expansion, right? You measure what you get. Yeah, you cannot say, oh no, I just want to measure the cosmological expansion. Okay, now what does it all mean, right? There was also like a big controversy. I mean, so Hubble's discovery is 1929, right? And there were the most popular models at that time were not the models that we are most used to now. The Big Bang model and all those were were not the most popular models. In fact, it was there, like Gamow did a calculation in 30s or something, and sort of suggested that if Big Bang was if Big Bang is taken seriously, all the matter would be closer and closer, and will be very dense early on, and dense and actually hot, because if you have an object which expands, it cools because of adiabatic cooling. First law of thermodynamics: expanding ideal gas, or expanding gas cools because of adiabatic cooling, right? So what Gamow, I think in 40 something, figured out is that if you take the Hubble expansion seriously and extrapolate back in time, it sort of suggests that the universe was dense and hot. And in fact, it could be as dense that it becomes almost like a star, being inside a star. The whole universe was as if everything in the universe is inside a star, extremely dense and hot. Okay, so it's shown schematically here. So basically, so it's shown schematically here. So we are here. So the good thing about light is that it has a finite speed. Okay, so if we are seeing the sun, if we are observing light from the sun now, it's not reflecting the status of the sun now. It's reflecting the status of the sun 8 minutes ago, how it was 8 minutes ago, because of the finite propagation time for photons from the sun. It does not just apply to the sun. You can just go, the farther the object is, the earlier you are looking at it and you're observing it now. Okay, so for example, the Milky Way has a size of, say, 10 kiloparsecs, about 30 light years. So if you're observing a star at the edge of Milky Way, 30 light, no, not 30 kilo light years. So you're basically observing at 30,000 years ago. Okay, so it's a very powerful thing, and this is what enables us to figure out our own history. If this was not true, we could not know what happened to the universe earlier, right? Because you'll see everything now, right? So these laws of physics that we figured out on Earth in such painstaking manner becomes absolutely manifest when you go to these scales, right? Because it's totally different sort of regime of application of physics. Okay, so let's go back to this. This is your, say, WMAP or Planck satellite, which is trying to figure out whether there is a relic radiation or not. And you're sort of looking in all directions of the sky and trying to get photons, which are coming from as far as you can sort of get them from. What is shown here is, okay, so these blue balls and the red dots are basically protons and electrons. So early on, the universe was dense and hot. And if it was hotter than, say, 5,000 Kelvin or something like that, the hydrogen will get broken into protons and electrons. It becomes ionized. So this is the stage when the universe was totally ionized. This is before the last scattering surface, where the CMB comes from. Okay, and you can actually see the photons are sort of doing this random walk. They are not just freely streaming, exactly like in the stars. It takes a long time for a photon produced at the center of the sun to come out in the optically thin region. Okay, so here that's what is shown. And the photon, so with time, as the photon is moving, the universe is also becoming more and more dilute, more diffuse. And at some point, its temperature falls below the ionization temperature of hydrogen. Most of the hydrogen, most of the protons and electrons, which were away from each other here, combine and form these neutral hydrogen atoms, which are shown here schematically. They're like atoms. And once that happens, the electrons are all gone. And then the medium becomes transparent to light, to this light. Okay, so this is what is the CMB, right? This is the last scattering surface, and this happens about 400,000 years after the Big Bang. And since the radiation here is in such close contact with matter, they're like talking to each other, exchanging energy, momentum all the time. That's the condition for forming a black body spectrum. So this object, or this sort of last scattering surface, should have a spectrum which is very close to black body. It's sort of, almost like very simple application of physical ideas at this stage. Okay. Now, why are photons not free streaming here? Does anyone know? Like in this portion where the plasma is broken in, where the matter is in a plasma state, where there are electrons and protons just separate rather than being as atoms. Yeah, so it's essentially the free electrons interact much more strongly with photons compared to atoms. And in this regime, it's sort of Thomson scattering, right? If you have free electron and radiation, shown on that electron, that will make the electron oscillate, and it will scatter the radiation. So that is what is happening. This is Thomson scattering, very similar to Compton scattering. Compton scattering is just the high energy sort of version of Thomson scattering. Okay. So basically, we cannot see anything in light before this last scattering surface, because it's like we cannot see anything inside the sun through photons. In the same way, we cannot see anything through photons inside this last scattering surface. Okay, but there's a lot of physics that happens before this, which is sort of not accessible to optical telescopes, but there are other ways of trying to figure that out. Okay, now we know the physics of black body. This is like a very idealized representation of a black body. In textbooks it's written an ideal black body absorbs all radiation incident on it. All that is okay, but what does it actually mean? It's not helpful saying that an ideal black body absorbs all radiation incident on it. It's why should I care if it absorbs? The point is, a black body is a medium in which matter and photons are in equilibrium, right? They sort of collide. Photons, light and matter collide with each other and are able to efficiently exchange energy with each other so as to produce this universal black body spectrum. And in fact, this is the measured presently, like by COBE, was a satellite in 1990s, which measured the spectrum of the black body very accurately. And this is the black body spectrum fit. And look at the fit. This is one of the best black bodies, perhaps even better than you can actually manage in a lab. Okay, and look at the fit. The error bars are smaller, much smaller than the size of these markers. Okay, so this is why people take Big Bang cosmology so seriously. One of its biggest, most important prediction is sort of verified. Whereas in steady state cosmology, it's very difficult to get this. You have to tweak things and so on. Okay, this is like, I'm sure you all know about this. This is our sun. This is where, energy of the sun is produced at the center. Photon is produced there. It gets scattered, absorbed, emitted. The same photon will not come out here. Right? It just is absorbed by matter, emitted more by matter, and so on. And here the temperature is 10 to the almost close to 10 to the 7 Kelvin, right? So the photons here are much hotter compared to here, but since there is a temperature profile in the sun, as they come out, they also sort of come in equilibrium with the local surroundings, and they sort of become cooler. And this is a very simplified picture. But once it comes at the photosphere, it's zoom. After that, it takes it 8 minutes to reach us. But before that, this time is of order, 50,000 years. So 8 minutes after this and 50,000 here. Sort of amazing, isn't it? Okay. So the black body, I really don't like this, the definition that an ideal black body absorbs all radiation. It just makes no, it does not convey anything. Okay, this is what a black body is, in which radiation and matter are able to talk to each other and establish this universal spectrum, right? So the radiation will have the Planck distribution, and the matter will have the Maxwell-Boltzmann distribution, right? Okay, so this is this yellow is the sunlight, the sun's spectrum measured at the top of the atmosphere, and this is a 5,250 degrees Celsius black body spectrum. You see, it sort of more or less does a very good job, right? But of course, not as good as the CMB. And you do see these, they're like ozone is still like farther up where this is measured. So you have absorption of UV from the sun by ozone molecule. You have the and this red thing is what's measured on the ground, and you see there are these, this red is what is measured. So you can see that because of different molecules like oxygen and water molecules, CO2, right? All the what do you call them? All the molecules that are responsible for global warming, greenhouse gases, right? They absorb all this radiation. No. When we say matter and radiation are in equilibrium, you have to have absorption and emission happening all the time, constantly. This just shows scattering. But that's why I'm saying this is a highly simplified way of looking at it. You have to have emission, absorption, and emission and absorption are necessary for you to establish black body radiation. Yes. Mm-hmm. Mm-hmm. That's right. It should be optically thick. Tau should be much bigger than 1. If you have a photon trajectory like this naturally means that tau is much bigger than 1. Yes. It need not have a high absorption coefficient if your depth is also large. That's good enough. All you need is a large tau nu. At that frequency, if tau nu is much bigger than 1, and you have both absorption, Kirchhoff's law tells us more the absorption, more the emission. A species like water molecule, if it absorbs very efficiently here, it will also emit very efficiently here. Okay, so yes, what you're saying is absolutely correct. That to establish a black body radiation, you have to have absorption and emission happening all the time. So there is exchange of energy, but the microscopic processes for matter radiation matter radiation interaction is this continuous absorption and emission of photons. So Milky Way, the name Milky Way means that why is this home of our sun called Milky Way? Well, what's so milky about it? Why is this name? And it's not just like Akash Ganga. It sort of conveys like the Indian name, right? It's Akash Ganga. Why is there this sort of a notion of something flowing like water or milk or whatever? Why is that there? Does anyone know? Why is this name there? Why is it not called, home of stars? Like, what are stars? Right. What are stars called in Hindi? In Sanskrit? Hindi. No, Sanskrit. Constellation. Okay. Tara Laya. Let's say. So just like Vidyalaya and Himalaya, why are we not calling it Tara Laya and calling it Milky Way or Akash Ganga? And what Ritik, is that the make it short? Dibya. Okay. What Guru also has a very long name, but Guru is much better. Dibya. So what Dibya is saying is sort of going towards that answer that yes, that the Milky Way appears like a sort of like a smudge on the sky, right? Like someone has just thrown water, thrown milk in some random way, which is sort of narrowly defined. Right? It sort of almost looks like a river. River is like a one-dimensional object in 2D space in some sense. So, so why does it appear like a diffuse smudge rather than a star, stars which appear like points? Why is that? No, it's not because of dust.
There are many stars and
Again, sort of Divya is going. Yes. Right. You're sort of going towards the right answer. So the right answer is the distance between the stars, the angular distance between the stars is smaller than the resolving power of our eyes. So the point is a single star, rather than being observed by our eyes as a point source, is spread over, right? I mean, that's just this Rayleigh criterion, right? The resolving power of an optical instrument is theta is lambda by d, where d is the size of the aperture. Now, you can also calculate the rough distance between stars, and it turns out that the distance between stars is slightly smaller than angular separate is slightly smaller than the resolving power of the eye. That's why the nearby stars, like the ones that we see at night, are pretty discrete, yeah. But the Milky Way we see as a band because they are at sort of 10 kpc away from us. And if you put these stars that far away, you cannot make out one from the other. It's sort of like a smudgy mess. So that's why it is Milky Way, via lectia in Latin. Via is road, and lactea, lactose is milk, right? So Milky Way. Okay. So anything else? Right. So Galileo, with his telescope, the telescope's aperture is much bigger than our eyes, was able to resolve some of the stars in the towards this Milky Way band in the sky. And then people figure out, okay, this is actually not some sort of a nebulous thing. In fact, it is actually made up of stars, which we see in our neighborhood all night. Okay. Okay, let's see. So, in fact, it's a good idea to do this estimate and to actually see. You can calculate theta is lambda by d. Lambda is 0.5 microns. D is what's the diameter of our eyes aperture and stuff. Just an order of magnitude. What's the mean distance between stars? Yeah, astronomy is actually a lot about such estimates than about like at the beginning doing heavy duty calculations. You have to know where you're going before you get into details. Okay, now we go to next lecture. By the way, this is a nice sort of web page where you can actually find terms related to astrophysics. Say terms. Let's say P. P Cygni, P cam, P CMB cam, P Cygni. So you will encounter terms when you read papers and books, and you will be overwhelmed. So if you find something, you can actually go to a place like this and put that in. Say, just tell me something that you guys want me to find. Where is the catalog location? Peculiar velocity. Yes, nice. How do I search it? Okay, let's go alphabetically. So peculiar galaxy, motion, peculiar velocity. Here it is. Peculiar velocity is the motion of an object with respect to the local rest. Rest depends on the observation and purpose. Blah blah blah. It talks about Hubble. So it then gives a link to Wikipedia and some other resources. So this is a good place for just finding out. And if you encounter something scary and you want to make progress and go beyond that first step, this is a good place. Okay. So in fact, a lot of my lectures will have such links which you should check out, okay, at leisure. Okay, now so we have sort of learned a little bit about the CMB. CMB, this cosmic microwave background, comes from all directions of the sky, unless something is blocking it, some other thing is blocking it. So what if you say that, okay, CMB is one thing which is very close to a black body. What about other wavelengths? Do we have such cosmic radiation coming from throughout all places in the universe, right? You can always say, okay, let me measure light coming from average in all directions and put them on such a plot. Okay, what is shown here is this nu F nu. This is like flux per wavelength, right? So nu F nu F nu is the flux per unit frequency, okay, and nu F nu is flux per unit logarithmic frequency. Let's see, actually, to show that, nu F nu is nothing but flux between a logarithmic bin in frequency or wavelength, actually. So this, of course, the x-axis here is wavelength. This is nu F nu. You'll almost always see, I'm sure you have already encountered this nu F nu in a lot of talks that you hear. And why do you plot nu F nu rather than just F nu? Right? F nu is the flux, but nu F nu. So F nu is energy per unit area, per unit time, per unit frequency. Right? If you make that per unit frequency, per unit log of frequency, d ln nu, that will give you d nu by nu. So that pulls up nu in the numerator. So nu F nu is the energy coming in an equal logarithmic interval in frequency, right? When you want to make a plot like this, it's a huge range in wavelengths or frequencies. So that's why you want to have something which tells you how much energy is coming between 10 to the 3 and 1 millimeter and 10 to the minus 9 and 10 to the minus 12 millimeter. So there's a reason why we use it. Okay, it's much when the range of values is huge, log scale is a better scale to use. This is extragalactic background, such a spectrum of not just the microwave region, but the whole spectrum that you can possibly access is called the extragalactic background. And you can see in terms of the energy, CMB sort of has the highest peak and the maximum area under the curve. So CMB, among the radiation fields, CMB is what dominates in terms of energy. Okay, so this is the first lesson from here. Here, you are at longer wavelength regime. Okay, so these are things like radio galaxies, hundreds of megahertz, gigahertz, that sort of a regime. And you see these are actually actual measurements put together. Okay, and this solid line here is the black body, the beautiful black body that the CMB is. Okay, so here you're going to gamma rays. Okay, so if even in gamma rays, if you look at random positions in sky, you have some radiation coming in. It's not as universal as the CMB. It's because of these active galactic nuclei, which produce a lot of radiation across all wavebands, from radio to gamma rays. Okay, so a lot of such AGN will produce this. Okay, and in every sort of even small region of the sky, if you go far enough, there are lots of them. So and the angular resolution in gamma rays is really poor. So it's sort of the same thing that happened to us when before Galileo, we were just saying, okay, it sort of looks like a milky thing. Again, here it's the similar kind of a thing that you're not able to resolve in a lot of these cases, the tiny objects like AGN which are emitting these. So that's why it sort of appears as a smooth background. So this is gamma rays and X-rays. The same is true for X-rays. X-rays are also coming from AGN, which are broadband emitters, active galactic nuclei, powered by accretion onto the massive black holes at the center of galaxies. Okay, even this portion, the radio, comes from accretion onto supermassive black holes. Right. This is where the stars are. Stars are black bodies. They are close to black bodies, and black bodies have a narrow range of emission. Right? It falls exponentially at high frequency, and at low frequency it has a steep power law, the Rayleigh-Jeans limit. Okay, so they're like pretty narrow in wavelength range. So these are stars. Now what about this stuff here? This is dust re-radiation in far infrared. A lot of galaxies, especially star-forming galaxies, have a lot of dust. What dust does is it absorbs a lot of UV and optical light. So dust is absorbing all this light, but it's also gaining energy from this light. So it gets heated up. Okay, and it gets heated up to 100 Kelvin or that sort of a temperature, and it emits as a black body. So the radiation coming out of a lot of these starburst galaxies are heavily reprocessed by dust, and that's why instead of appearing in the UV, right, massive stars appear in UV. These galaxies, dusty galaxies, starburst galaxies, are appearing very bright in infrared because of this dust reprocessing. In fact, it can reprocess most of the light that comes out in UV and optical, escapes the galaxy in infrared, far infrared, 100 micron and like. Okay. Anything else? So I think we have more or less covered. What's the source of things?
What's the difference between dust and gas?
Right. So dust are like particulate matter, like much bigger, like much bigger than molecules. Dust, they are micron size. There's a range of sizes of dust particles. Dust means the same in space, essentially almost like what it means on Earth, right? It's like a dust storm, right? And the appearance of ISM is like a dust storm happening all the time, and then there are patches in that dust storm which are sort of free of dust. That sort of is the picture. The absorption is actually quite heavy. Why is the flux more for the CMB? Because that's what we observe. And the question is, why is it? Because it's the if you do the calculation, right, the CMB, right, so this is the radiation which comes when the temperature of the universe at that time was about 5,000 Kelvin. That's when the protons and electrons recombine and form neutral hydrogen. But this is also high redshift. Redshift of the CMB, the age of the CMB, corresponds to about redshift of 1,100. Now the observed wavelength is 1 plus z times the wavelength of 3,000 Kelvin black body. So it gets sort of its peak at around this a millimeter wavelength. It's called microwave, but it's actually peaking at a millimeter. And you know, why is it so bright? Because that's how the whole universe emits, right? So there, all the light from that era of the universe, which had such a high energy density, comes in this. So it has to be bright, because that's the the whole universe is actually producing this. Okay. And if you plug in the numbers and do the calculation, this is about right. Okay. Right. So it's actually not that hard to do, right? You take a black body at 3000 Kelvin, and it still sort of requires a little bit of cosmological knowledge, but not hard to do. By the way, the number of CMB photons here per unit volume is about 400 CMB photons per centimeter cube. Right? It's actually a very large number of CMB photons per unit volume. The number of atoms, say hydrogen atoms in the ISM, is like 0.1 particles per cc. So there are 400 times more photons per unit volume than particles in the ISM. And ISM is one of the densest portions of the gaseous universe. Huh? Cool. Okay. How does our Milky Way look like in different wavebands? Okay, so in fact, I have not put references to a lot of figures. They are from the internet, and in fact, if now I'm sort of recording these and putting up publicly, but there is no bad intent here. A lot of this is from Wikipedia and Google Images and stuff, but yeah. So that's just a disclaimer. So let's see. So if we look at the Milky Way, so you can go and look at our own Milky Way from radio to millimeter to far infrared to visible and so on. How does it look like? This is in galactic coordinates. So in galactic coordinates, the Milky Way is horizontal. So this is the galactic center. Okay, and this is the galactic center. This is anti-center. So this is the anti-center. And what you're doing is just sort of making maps of radiation in that waveband. So this is 408 megahertz survey by telescopes in Bonn, Jordan Bank, and Parkes, and so on. So this is radio imaging, and this is radio continuum. So what's the source of this radiation? It's the synchrotron emission by relativistic electrons in the halo of the Milky Way. You have learned about synchrotron radiation, right? Synchrotron radiation comes from relativistic electrons. Okay, so the relativistic electrons gyrating around magnetic fields produce a continuum of radiation. Unlike a black body or something which is very narrow, here the spread of radiation over frequency and wavelength is broad. So that's why these are continuum. Unlike lines, you have radiation coming in very narrow wavelength region. Okay, so this is radio emission. This is 21 centimeter maps. The same thing, same portions. You look at different wavebands. You see, this is very diffuse. You see light from very far away. This is this is longitude, and the transverse direction is latitude.
Vertical scale.
It is very thin. I actually don't remember. It sort of is less than 5 degrees. It's very, very small. It's almost just looking at the galactic plane. Okay. Yes. Name first, and name. Yes. Both. You have disk and the halo. And this is lower frequency. I mean, these electrons are produced in the disk, but they also, get transported in the halo. That's correct. So when I say halo, I mean like near the disk. Yes. You're right. Like this and this this radio continuum at 2.4 and 2.7 gigahertz. This is much narrow. It's the same mechanism, synchrotron emission, but this is much thinner, less spread out, because higher energy electrons cool very fast. So they are not able to diffuse away this much. They cool away, lose their energy before they move away so far away. Okay, but it's the same mechanism, same sort of a little higher energy electrons will produce higher frequency. Right? The radiation, the peak of the synchrotron emission goes like gamma squared nu cyclotron, right? So gamma squared. So the larger the gamma, the observed frequency is higher for the same cyclotron frequency. Okay. So this is 21 centimeters. This is not continuum. This is a line. This is the famous hyperfine transition, the forbidden line of neutral hydrogen. Okay, this is molecular hydrogen, 115 gigahertz. So we are going towards higher frequency as we go down. Molecular hydrogen basically is tracing very cold, dense gas. It's traced by CO, carbon monoxide. H2 being a molecule without a permanent dipole moment, it does not have strong radiative properties. It does not radiate as efficiently as CO, even though CO is extremely underabundant compared to molecular hydrogen. It produces more radiation because of its permanent dipole moment. So these are rotational lines of CO. You are mapping it here at 115 gigahertz. This is infrared. This is basically, far infrared. This is reprocessed dust, reprocessed emission from stars coming from the dust. This is near infrared, like, a few microns. This is stellar light from old stars. Old stars are lower mass and they are redder, so they emit in infrared, and there are a lot of them. So this optical is, you see in optical, you have these bright regions, but there are a lot of these dark lanes. And what do you think those lanes are because of? Dust. So, you see there's a lot of dust which just comes in our way and prevents us from seeing, far at all. This is X-rays, 0.25 to 1.5 keV. 1 keV is about 10 to the 7 Kelvin. Okay. So this is very hot plasma, and it's most likely created by supernova remnants. And there are these point sources which can be accreting black holes, like low mass X-ray binaries and high mass X-ray binaries and things like. So there are point sources. You can actually clearly see here. And there's also diffuse stuff. Diffuse stuff is perhaps due to supernova remnants. Point sources are due to these black hole, galactic stellar mass black holes. I'm not talking about the galactic center supermassive black hole, but even that is an X-ray object that also emits in X-rays. But it's not that bright. It's not like it's one of the dimmest black holes that we know of for some reason. Our Milky Way black hole. Okay. Then gamma rays. If you go to gamma rays, this and this look very similar. So gamma rays are produced. To explain this, the gamma rays basically are produced by cosmic ray protons. So there are relativistic protons which are called cosmic rays, and these cosmic rays are diffusing in the Milky Way and beyond. But in the Milky Way, the number density of nucleons is high, right? And cosmic rays interact with other nuclei, like nuclei in, say, molecules, like H2 molecule or neutral stuff. Wherever the density is high, these cosmic ray protons will give rise to pions, and those pions decay, producing gamma rays and neutrinos. In fact, so there was a recent announcement of neutrino map by IISc for our Milky Way. They were able to see neutrinos from the galactic disk. So this is, neutrinos are not put here. This is just electromagnetic radiation. Okay, let's go. Let's see how much time do I have. Okay, we have 15.
Oh, all the
difference in the spectrum is just that X-ray you don't see a disk clearly, and in everything else you can clearly see a disk, like a thin disk in all the other parts.
That is correct.
So why would X-ray alone be missing?
Right. So even in X-rays, if you look at a little larger scale, you will see, you will see it's a little more diffuse. So if you look at E Rosetta maps, E Rosetta is this 2-year-old X-ray telescope, and it has made an all-sky map. You see things called Fermi bubbles and all that. So yes, it's a little more diffuse. It's because X-ray gas is much hotter, much larger volume. Cooler things like to will have a smaller scale height. So like CO is the thinnest because it's the coldest, densest stuff. Okay, yeah. Yes, so the brighter things are white, I think, yeah. And the dimmer things are, except perhaps for this one, this is a grayscale. Right here, white is bright and black is dark, less brightness. Okay. So at these energies, it's sort of supernova remnants in Milky Way and other sort of stellar related processes. But yeah, the cosmic rays, if you go to very high energies, they are perhaps from AGN and stuff. So it's complicated. Okay, stars are close to black bodies. We've already sort of talked about it a little bit. This is the Planck spectrum. The specific intensity for a black body of temperature T is a universal function given here, right? Specific intensity. Do you guys remember your radiative process? Specific intensity is the most fundamental description of a radiation field, the classical macroscopic radiation field. Okay, and so the specific intensity of a black body is universal, and it only depends on its temperature. It has a universal spectrum as a function of frequency or wavelength, and that is called Planck function. And the color of the black body, characterized by the wavelength at which the maximum light comes, lambda max, satisfies this Wien's law. And say for the sun, which is at 6,000 Kelvin, the lambda max happens at 0.5 microns. So this is the way I remember Wien's law, rather than that number which I don't remember. I know the sun is 6,000 Kelvin and it peaks in yellow, green, 0.5 micrometer. So this is a good way of remembering it. So if you want to put it for the CMB peaks at millimeter, so the temperature will be proportionally lower, 2.73 Kelvin. You know that. Okay. Okay, so this is the more detailed description of black body radiation. This is something we also know, that energy emitted by a black body per unit area per unit time is sigma T to the 4, which is called Stefan-Boltzmann law. This is also universal. All black bodies emit like this. If you double the temperature, the flux increases by factor 16. Okay, this is essentially nothing but integral over frequency. Right? If you integrate this equation over frequency, you know how much it is radiating totally across all wavelengths, which is nothing but this. Okay, so it's a homework problem. Go from here to here and express this sigma in terms of more fundamental parameters like Planck's constant and Boltzmann constant, right, and speed of light. Okay. Yeah, it's a good idea to have a feel for what color these different objects are, like white dwarfs. Are white dwarfs cooler or hotter than the sun? Who thinks cooler? Raise your hand. Cooler? No one. Okay, good. Yes, white dwarfs are hotter than the sun normally, and red giants, cooler. They are like red, and color red tells us the temperature because they're all black bodies. The sun, of course, we know it's 6,000 Kelvin. Planets are, of course, cooler, and so on. So you have to have a sense of all these different beasts that appear in this zoo. Spectroscopic classification of stars. Stars are not perfect black bodies. Okay, they are close to black bodies, but there are a lot of spectral features in them. So, for example, here is a bunch of spectra of stars in optical light. So this is something called an O5 star, and you see its peak, its lambda max is not in optical, it's in actually UV. So it's a very hot star because its lambda max is in UV. This is an A1 star. It sort of peaks in 4,000 Kelvin. And you can actually see these like absorption lines, absorption features in all of them. And just by looking at spectra, you can actually, figure out their temperature and mass and all that. That's the subject of stellar structure. Okay. So this is an A star. This is a G star. The sun is a G star. So this is like close to the spectrum of the sun. And you can actually see these are those lines, perhaps those lines identified by Fraunhofer when he sort of saw these dark bands in the spectrum of the sun. This is sodium D line, one of the Fraunhofer lines. These are calcium H and K lines, which is also very deep and important lines in the sun, very prominent. This is this is a K star. K is smaller, less massive than the sun, and you see as progressively the peak lambda max shifts to optical and beyond infrared as you go to lower mass stars. So this is called spectroscopic classification of stars. There's like a whole lot of physics going on here, and Saha, Meghnad Saha, whose ionization formula and so on we are sort of are familiar with, was the one who gave the physics, the statistical physics of this formation of these lines. Okay, so it's not like our sun has very large abundance of calcium too, compared to say this O star. It's not like the sun has like 100 times more calcium in fraction compared to this O star. It's not just the abundance which cause the depth of these absorption lines, it's also the conditions. Every ion is produced in abundance in a certain temperature and density range. Okay, and that's what that Saha's famous formula gives. What will be the ratio of these abundance in different ionization states. So all this work was done much earlier. People had classified them. Okay, this is how a K star looks like, and and so on. The interpretation of this sort of required physics. Okay, and that's what's provided by Saha's calculations, and of course followed up by a lot of detailed things. Here you have these Balmer lines, absorption lines, H beta, H alpha, 6,600 Kelvin, 6,600 angstrom, H beta, H gamma, and so on. So n equal to n to 2 transitions, the Balmer lines, right? Hydrogen, what are these? Lyman, Balmer, Paschen bracket, all these things. So these things were studied for more than 100 years before they were figured out what they were, and just classifying them, laid the foundation for making them understandable. Okay. So this is the classification of stars: O, B, A, F, G, K, M. O are the most massive, hottest stars. M are the M stars, lowest mass, coolest, like 3,000 Kelvin or so. And there are also L stars and brown dwarfs and so on. And going to the planets, they are even cooler. Right. So this is for an individual star, but a galaxy is made up of a lot of stars. So a spectrum of a galaxy is like the sum of spectrum of all the stars that it contains, plus reprocessing by the dust. That's extremely important, right? As I said, 95% of a lot of starburst galaxies, light is reprocessed by dust. So the question is, if we see the spectrum of a galaxy, can we figure out what is the stellar population in that galaxy? For example, all these JWST results, you see early spectra, photometric, observations in different bands. Can you figure out what's the nature of their stars? What's the nature of their absorption? Is there dust in those galaxies and things like that? So that subject is called stellar population synthesis. Given a spectrum of a star cluster or a galaxy, can you figure out uh, how many stars of what mass do you have? How much dust do you have? What kind of dust do you have? What is the age of the stars? When did the stars form? And so, what's the metallicity of the? There's a huge range of questions that you can try to address from the observed spectra. Spectra are extremely powerful, right? Uh, a spectrum does not make a beautiful image like that we are all used to, and HST images and all that, but they tell us a lot of physics information. Okay, so this is the power of the spectra, and to figure out the physics of uh, galaxies, we need the stellar population synthesis, and for that there are like different ingredients. There are different ingredients. One of the ingredients is called something called the initial mass function. This is have you guys covered initial mass function in a course? Mass function of stars. So initial mass function is a simple idea that uh, if 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 a population of stars form, like a star cluster is born now. I mean, when I say now, I mean now is a delta t of order mega years, right? In astronomy, the time scale, the shortest time scale is actually, at least in this kind of astronomy, is million years. Stellar, even the most massive stars are on the main sequence on a time scale less than a million year. So if you have a star, family, a star forming region now, what is the number of stars as a function of their mass, right? That is what quantifies the initial mass function. So dm, number of stars per unit volume per unit mass, is proportional to minus m to the minus 2.35. This is the famous Salpeter IMF, Salpeter initial mass function. And this is sort of obtained from observation. You try to do this exercise using observations. So this is an example of how you would measure. So a lot of these figures are actually from that book, uh, uh, Spark and Gallagher. I said there are 3 books that we'll be following. This is SD. I'll be calling it SD, Spark and Gallagher. So these are the data points. You just sort of look at some, say, this is per 1000 parsec cube per magnitude. So you look at 10 parsec by 10 parsec by 10 parsec cube around the sun. Okay, and just look at the spectra of all the stars, all the stars, and ask what their luminosity is in the V band or their absolute magnitude in the V band, and make these bins. Okay, and just sort of calculate this phi of x, where x is this x-axis. So how many stars are there between absolute magnitude mv minus a half to mv plus a half? Okay, and you put that number and you put the error bar, because if you just observe, say, one star, it could be 0 or 1. There is an error bar which you have to put just because of the statistical fluctuation. And if you do all that, this is what you observe. Okay. Now you see that there are a lot of stars with large values of MV. Large value of MV means lower luminosity. Remember this minus 2.5 log factor in magnitude to flux versus luminosity. This is not flux. This is the actual luminosity, because it's absolute magnitude. So the number of dim stars is much more than the number of luminous stars. Okay, so this is what you just measure. Okay, but you also know the theory of stellar evolution. You know that massive stars evolve off the main sequence much faster and become black holes and neutron stars. So there is a recipe to go from this measurement to the mass distribution, right? So the mass will be slightly more biased towards more luminous things. And this is the luminosity distribution. How much light comes from stars of this luminosity? Okay, and you see this is peaked in, at very large value. So what it means is that most of the light of a galaxy is coming from the, I mean, if there is no dust, that is, it will come from the most massive star. But most of the mass will be in low mass stars, and the number, of course, is dominated by low luminosity stars or low mass stars. So mass and luminosity have like 1-to-1 correspondence. Okay. There's another thing that here you are normalizing it with the denominator, right? If you have dimmer stars, less luminous stars, you can only see them out to a lesser distance, right? A very bright star, you can see much farther out. So you have to divide this by the maximum volume over which you can see some population of these stars. Okay. So since you know since you know the luminosity and you know that how sensitive your telescope is, you know this is the distance out to which I can see O star or a, right, you can see an O star much farther out, right, compared to say M star, right? Okay. So this is something called the present day mass function, what you measure now in some region. But this is not how the stars, or this was not the population of stars when they were born. There were many more massive stars, and a lot of them just evolved off the main sequence, and you cannot see them anymore. This is the present day mass function, right? Sort of the same data in this grayish shade. This is the present day mass function. Now you know the stellar evolution theory. You can say that, oh, this star, has evolved off. You know that you don't see any, say, O star or B star. You know the age of O and B stars from your stellar theory, stellar evolution theory. Say, okay, if you don't see any O stars, and if you have, say, thousands of stars there, you should see them. If you are observing it at t = 0, you should see those O stars. But the fact that you don't see them means that they have evolved off. And that tells us what the age of this stellar system. Okay, so here, for example, this is this psi mv is the actual initial mass function at t = 0 when the stellar population formed. This phi ms is the present day mass function. So if the main sequence lifetime is longer than your time at which you're observing, right? If the main sequence, so all of those stars will be on main sequence. So the two are identical, right? The present day mass function and the initial mass function are on top. So here you don't have two lines. Here you have two lines. Okay. If your main sequence lifetime is less than the age of your stellar population, then the initial mass function is bigger than the present day mass function by this factor. And this factor is nothing but your time since the starburst divided by the main sequence lifetime. Okay, so all these guys are bumped up, right? And the more right you go, the larger the bump up is, because they have even shorter main sequence lifetimes. 110. Okay, so let me actually quickly just cover this star portion. So I'm actually hoping that you know about stars already, because this course is not about stars. It's about galaxies. Oh, you have the 2 p.m. class, right. So just less than 5 minutes. Okay, this is something called the HR diagram or Herzsprung-Russell diagram, which basically distributes the luminosity or absolute magnitude as a function of the spectral class. I told you different stars have different absorption features, and you can actually put them in spectral classes. And the spectral classes actually correspond to a temperature, effective temperature, right? Say A star had those prominent Balmer lines, but that was sort of the black body, the continuum behind that was peaking at 4,000 angstrom. So in the same way, there's a one-to-one relationship. And stars sort of lie in this, these are main sequence stars. They are burning hydrogen in their cores. That's where they spend most of their time. And depending on their mass, they evolve off and do various things. I'm actually hoping that you know about this reasonably well, okay? Because this is like foundation of the stellar population synthesis, which I was mentioning to you about. If you don't, you actually at least read the book, this Gallagher, Spark and Gallagher book. This is like a table of the mass and luminosity, effective temperature of the star, spectral type, main sequence lifetime, time that it spends on the red giant phase. This is the total luminosity times the main sequence age. For example, for the sun, which is here, its luminosity is L sun, of course, and it has an age of 10, age of 10 gigayears. So this is about 10.8. This is how much luminosity comes out in the post main sequence phase. So all this is physics of stellar evolution. Okay. And this is my last slide for this class. Okay. This is say an IMF, initial mass function. I told you initial mass function is a key ingredient for this whole stellar population synthesis. So here in the red line, we have the saltpeter IMF. Okay, so this dN/dm is m to the minus 2.3. That's like that fits reasonably well a lot of observations. And there are other kind of IMFs here, the Milky Way IMF and the bottom heavy IMF. Bottom heavy IMF means that there are top. So bottom means heavier things. So there are many more heavier stars than the lighter stars, right? Bottom heavy, the guys at the bottom, the heaviest ones, are more numerous. So this is a bottom heavy IMF. Once you have the IMF, this HR diagram. How much time does a star of a given mass stay on main sequence? How it evolves off it, and so on. This is that physics, stellar evolution physics. This is the HR diagram. These are something called isochrones, right? The locus of equal age. So the stars. So this is 10 to the 6 years, and this is what happens at a longer time. So these are isochrones. So for a given mass, how if they started at this time, where would they be on this? This is the stellar spectra. We also saw stellar spectra, like A star, it looks like this, and so on. So these are the physics elements that goes into this simple stellar population. So IMF convolved with stellar spectra, convolved with where they lie on this HR diagram, give you something like a spectrum. This is F nu versus lambda, right? So if you have an older population, it will be peaking and infrared, right? If you're observing these stars now, like very early on, it will have a lot of optical and UV. This does not have dust yet. Okay. Now then you put dust processing and chemical evolution. So this x-axis here is 15 gigayears. So you start with the population and then you pollute it with metals and all that. All this basic elements of stellar evolution, elemental pollution, and all that goes in, and then finally you produce this. This is nu F nu versus lambda, and this blue is what you would get if there were no dust, and red is what you would get if there is dust. It's totally changed. Okay, and JWST data will give you something which you try to match with this red line. And you will change your parameters, IMF, you will change the dust and blah, and try to see, okay, I get a good fit. So then you will say, oh, this galaxy had this star formation history, and this kind of an ISM, it's dust free and so on. So this is the power of stellar population synthesis. It is behind the interpretation of the observed spectrum. Sorry, I'm actually going to end here, and I think you guys go for lunch. Thanks.